Hello, higher algebra students, here with Unit 7, Lesson 2, Forms of Quadratics. This is the first of a couple lessons around forms of quadratics. And before we jump into the concepts of this lesson, let's just do a quick recap here. So this is just the kind of the main areas that we're going to be continuing to look at with these quadratics here. So you can see here's a graph that's already given to you. Has a vertex point here at -3, -1. It is an x squared graph, so the graph actually originally is x plus 3 squared minus 1. That's actually the original graph. And so just as we look at the points here, we see the vertex that I just marked as the -3, -1 point. The y-intercept up here, again, all y-intercepts have a 0 in the x value, because that's what makes them a y-intercept. And then the y value there is 8, so the y-intercept is at 0, 8. The x-intercepts, which again have a couple gray dots here, I'll use a different color here now, but that is at -2, 0, and this here is at -4, 0. So those would be our x-intercepts. Again, x-intercepts always have a 0 for the y value. That's what makes them an x-intercept, is because the y value is 0. The axis of symmetry here, you can see the vertical line that would cut this right in half is right up here. And again, that axis of symmetry being a vertical line would be an x equals equation. So this is just x equals -3 would be our axis of symmetry. Our domain, I know you can't see here, but this is just a picture cut off. There are arrows there, so this continues going on forever. The range, you can see, would minimize at a -1. That is the floor. The ceiling there is infinity as that keeps going up. In terms of where this is increasing and decreasing, where it's increasing, again, would be any area where it's going uphill, which you can see starts at that -1 point. But again, at -1 is actually staying horizontal. So this would be, at -3 for x, it's actually staying horizontal. So the increasing there actually runs from -3 to infinity. It will continue to increase forever. But again, the -3 has a parenthesis. We never use brackets for increasing and decreasing, because that point at -3, 1 is actually not going up or downhill. It's just flat at that point. Decreasing here, then, it would be, again, it's coming in from the left. So it's coming in from -infinity in terms of an x value for where it's decreasing. And it ends the decrease at -3 again. So you can see both of those -3's have parentheses, because the actual point -3 is neither increasing nor decreasing. And again, these are always x values that we're looking at when we're talking about increasing and decreasing. So just a little recap before we jump into the actual form of quadratics here. So we have three main forms of quadratics, and understanding what each one of these accomplishes is going to be most notable as we move forward through this unit. So we have a standard form, which is kind of that the form that you've probably seen a lot, where it's a 3x squared plus 2x plus 5 or something like that. And a couple things that this really does a good job of telling us is this c is the y-intercept, just like we would see in an mx plus b, but now it's a quadratic. There's a parabola involved and so forth. So that c becomes our y-intercept, just like the b was our y-intercept previously. And then the scale factor will come into play later on as well. And the scale factor is that a that's at the beginning here. That will be important as we move forward. The factored form is the second. And again, the factored form is really good at telling us the x-intercepts. Okay, the x-intercepts are going to be the points where each of these equals 0. So x minus p equals 0 and x minus q equals 0. So we'll get into that. So you can see the actual values of the x-intercepts will be p, 0, and q, 0. And again, for instance, if this one here were x minus 3, that means the x-intercept would be at 3, 0, because the minus is built in. And what it really is saying is when you put a 3 in for x, that's what makes it equal 0. So that helps us with the x-intercepts in factored form. And again, that scale factor exists out front as well. Finally, vertex form. Not surprisingly, vertex form does a good job of helping us find the vertex, which again is in a parabola. The vertex would be the minimum or the maximum depending on if it's a smiley face or a frowny face, if you will. Open up or open down is what that's called. So that vertex, that point, HK in each of these is something that we get from the vertex form that's really nice. Scale factor is there as well, and it will tell us the axis of symmetry, which is just at x equals h. Again, that's meaning the x value is that vertical line that goes right down the middle of these graphs. Right, so when we look at this now, part of this is kind of identifying what form we're in each one of these. And so, for instance, to recognize that we're in a factored form, into a vertex form, into a standard form, and so forth. So you can see these factored forms here that we have, and we want to put them into a general form or a standard form. And to do that, we're going to use things like distributing and foiling and so forth. So when we distribute here, this x times 3x, that's a 3x squared. X times 4x is a plus 4x. And then, of course, technically, there's that plus 0 to make it the standard or the general form. So that would just be converting the factored form into that standard or general form. On this top right one, this is where we have that FOIL, which is first. So x times x, which is x squared. Outside, which is the first one and the last one, so that's x times 5, so that's just a plus 5x. Inside, which is a negative 1 times x, that's negative 1x. And then last, which is negative 1 times 5, or minus 5. So from there, we just combine the like terms, and we have now x squared plus 4x, since it's 5 and a negative 1, minus 5, and there's your standard or general form again. And we see the y-intercept, and we see that leading scale factor, which in this case would just be a 1, since it's 1x. Here it was a 3. So that's that a term that we're referring to on the previous slide. Third one here, again, this is just distributing. Negative 2 times 4 is negative 8, and it's x and an x, so that's x squared. Okay, so again, you're multiplying the numbers, and x times x is x squared. Then you have negative 2 times 1 is negative 2x, and again, we can tag on a plus 0 as our y-intercept there. But again, now we've got that leading term of negative 8, and we work from there. Last one here, just again, a quick FOIL. First is 3x times x, or 3x squared. Outside is 3x times negative 2, which is a negative 6x. Inside, which is a positive 4 times an x. And then last, which is 4 times negative 2, negative 8. Combine those like terms again, and we've got a 3x squared minus 2x. Again, that's combining the like terms there of negative 6 and positive 4, and then minus 8. And so we've got that y-intercept, we've got that leading term of the 3 in front of the x squared there. So those are all, again, when we have it in factored form to begin with, that's going to be really helpful for those x-intercepts as we start to calculate those, where it's going to be 0. And then we eventually move to the general form, and that's going to be really good for the y-intercept. So each of these versions presents its own kind of positive for us as we try and solve certain specific elements of these quadratics, like we did on that warm-up. Here again, finding the x-intercepts using the zero product property. So this is just a little more on how we utilize this factored form to find those x-intercepts. Again, that was the big benefit of the factored form. And again, the zero product property now is the idea that when you multiply or need to multiply these terms to have them equal 0. So for instance, term A here and term B here, in order for those to be multiplied to equal 0, one of those terms has to be 0 on its own. Okay, because obviously anything times 0 is 0. But if one of them's a 1 and one of them's a 5, then you can't get it to equal 0. So that means either x plus 3 has to equal 0, or x plus 2 has to equal 0. So what that really means for us is we just subtract 3 from both sides, or subtract 2 from both sides. That means that one of these two has to be true, which means our two x-intercepts are at and I'll change colors here, would be at negative 3, 0 and negative 2, 0. Now, I know it was an or to begin with, but what this just really means is one of those two is going to have to be true. And so when we graph, when it has the full line, it will cross at both of these spots, because in the end, that's what makes those x-intercepts, is that at negative 3 at 0 and at negative 2 at 0. So those are really both x-intercepts, but again, for the zero product property, we just really need one of them to be 0, but that doesn't mean that only one of them is an x-intercept. For the second one here, again, this leading 2 here really doesn't influence the x-intercept piece, because we still need either x plus 5 to be 0, or we need x plus 3 to be 0. And of course, we can subtract the 3 and the 5 from both sides here. So it's x equals negative 5, or x equals negative 3. So our x-intercepts here are at negative 5, 0, and negative 3, 0. So again, just using that zero product property to show where our y value would be 0, which is the y values are these here in this case. Next one here, as you look at this, where we don't technically have a second addition or subtraction here, what this just means is that either 3x has to be 0 or x minus 6 has to be 0. Okay, and you can divide by 3 technically here if you want, but that just means x is 0, or as you add 6, x is 6. So our x-intercepts here are actually at the origin of 0, 0 and at 6, 0. So those would be the two x-intercepts in that particular problem. Now this last one here is probably the most complicated of all of these, but again, all we're really doing here is saying that either 2x plus 7 has to be 0, or 5x minus 1 has to be 0. So the x-intercepts then, of course, would be the result of each of those, because there would still be two x-intercepts as we think about in all these graphs. We're looking at something that's like this, where it crosses the x-axis in two different spots. So we solve these. As I solve this one on the left, we get 2x equals negative 7. We divide by 2. So x equals negative 7 halves, which means negative 7 over 2, or negative 3.5. 0 is one of our intercepts. And then the other one, we add 1 to both sides. So we get 5x equals 1. We divide by 5. So we get x equals 1/5, which means the point, sorry about that, the point 1/5, 0 would be our other x-intercept there. So then we have our two x-intercepts there at negative 7 halves, 0, and 1/5, 0. And again, this is why that factored form is especially helpful, because we use this zero product property. We solve each part as though it were equal to 0, and that gets us those x-intercepts. So this again is really the biggest value add in that factored form, as each one of those three includes its own value. Again, that was back in that original gray slide of the value of each one of these. So here, this is the factored form. And lastly here, just as you're looking at these in Schoology, some things to think about are really kind of how you put these in. So if it's a plus or a minus, you're going to kind of put that in with these terms. So it'll always kind of have the x squared and the x and then the final term. And you'll put that leading value, that value in front of the x squared, and then whatever the x is, in this case it's minus 2, so you'd put negative 2. And then that final c term, which in this case is plus 9. For this one here, you can see there is no x term. So that would be plus 0x. That's what having no x term means, is that there is no x. So you can just put a 0 in there. The negative 3 is that leading term that goes there. And then finally, the minus 10 goes at the end. So just a heads up there on how you'd type these in. Looking at some last things here, just again, here's some pictures where you see the x-intercept. Again, make sure the x-intercepts are at a point here, not just saying negative 2 and 4. This is the point negative 2, 0. This is the point 4, 0. So make sure that you note that with the x-intercepts. And then with quadratics, they can have up to at most 2 x-intercepts. But sometimes there are less. You can see here there's no x-intercept since when the whole graph is below. Here you can see the intercept is actually just at the point -2, 0. So there's only one x-intercept in that situation. So just be aware that the x-intercepts, there could be 0, 1, or 2 of them, depending on where that graph resides. Thank you for listening, and as always, please ask questions if you have them.